Hello, good afternoon. I'd like to begin by thanking Abhishek Da and other organizers for the opportunity to visit ICTS and attend this very timely workshop on very interesting topics. So I'm going to tell you some recent work that provides a new angle to a very well-known phenomena, which has been studied for half a century, if not longer. And the work was mostly done by my excellent student, Xiuwen Wang in Beijing. And so we have a picture of this CSRC located in the suburb of Beijing. And actually some of you in the audience, including Sriman, visited some time ago. And actually our institute runs in some ways similar to ICTS. So we have very active visitors program, and also we host workshops and conferences from time to time. So I hope to see all of you there at some point in the future. So these cartoons on the right, actually two of these are taken from a very nice book, which I like, by Philip Nelson. Serve as a kind of a reminder, for me at least, that when we think about biology, we don't always have to think in terms of very complicated biochemical networks, but maybe also in terms of energy. And we know living systems can only function with some energy source. So this is also one of the underlying themes behind this particular work. So I'm going to start with a couple of videos. And this is actually an old video showing you the oscillation in yeast suspension. Actually, in order for the yeast cells to go into this collective mode, you have to prepare them in a kind of a special way, and you have to starve them for maybe a few hours, and then you have to do a few things which I don't quite understand, and then you get them into this oscillatory mode. I'm going to come back to this a little bit later. And this is another example which has been published by Thomas Greger's group at Princeton and his collaborators about dictee. And you know, the dictee, they have a very interesting life cycle. At a certain stage in their life, they actually have to send out signals to each other and then aggregate and form a spur and then go elsewhere. So this oscillation actually serves as a so-called quorum sensing. So it's a way to actually detect how many other cells are in the neighborhood. And then when there's enough density, then they start to aggregate, move in a particular direction. And eventually, they can form the aggregate. So these are some experimental measurements on these cells that show the collective oscillation behavior. So in the previous video, for the yeast suspension, the period of oscillation is less than a minute, something like 40 seconds. But in the case of this amoeba, then the oscillation period is on the order of 10 minutes. So now this kind of oscillatory phenomena has been studied for a long time, and there have been many theories proposed for why these individuals can together produce some group behavior like oscillation. And one of the most famous models is the so-called Kuramoto model. Actually, I think almost 2 years ago, there was a conference dedicated to Kuramoto's work. And then this is something I took from their webpage describing the workshop. And then the organizer said that in the studies of oscillatory dynamics, the Kuramoto model plays the same central role as the Ising model in the studies of phase transitions. So at least up to very recently, most people, at least in our community, when they think about this kind of collective oscillation, they will first go to the Kuramoto model. And of course, the whole point of this talk is to show that maybe we can go beyond the Kuramoto model. Anyway, so this is just a quick reminder of Kuramoto model, which I'm actually not going to talk too much about here. So in the Kuramoto model, this collective oscillation is seen as a synchronization phenomena. So there, you already assume that individual units, they are on some kind of an oscillatory state, doing some kind of a limit cycle oscillation with each with its own period. And now if each of these oscillators going with its own frequency, then the group as a whole, if you look at something like the order parameter, which is the average of the phase factor from individual cells, then you're not going to see much of a signal if the phase of these individual units are spread more or less uniformly on the unit circle. But due to the coupling, when the coupling becomes sufficiently strong, then there's a well-known phase transition in this system. And beyond this coupling strength, then a subset of these oscillators, they're going to get synchronized and move with the same frequency. And also phase-wise, they tend to cluster. And this way, this so-called global order parameter will assume some finite value. So that's basically the physics behind this synchronization phenomena described by the Kuramoto model. Now, in the case of, there are many examples people have looked at, and in many cases they try to say that the experiment really corresponds to this Kuramoto model. But if you look at things more closely, then you find a lot of other things which doesn't quite fit. In particular, in the real situation, if you have really cells, each cell is somewhat different. And more recently, there are, so I'm just jumping ahead, so-called microfluidic studies that allow you to look at the oscillation or non-oscillatory behavior of individual cells under very well-controlled environments. And normally, this kind of single cell measurements give you some time series of the, for example, intensity of some chemical inside the cell, in this case, NADH. And then you see that each cell shows somewhat different behavior, but not necessarily that they are going with different frequencies. In fact, in some cases, when you don't have an external periodic signal to drive them, then some of the cells, they actually have some kind of internal oscillation, but of course that cannot be perfectly periodic because of the noise involved. But some other cells in the population may simply don't oscillate at all. And of course, you can try to synchronize the oscillation by through this microfluidic setup to have some kind of periodic control of the external condition. For example, the concentration of some chemical in the fluid that you flow through the system. And this way you can synchronize the cells, for example. And now if you look inside the cell, then you find very complicated biochemical pathways. So exactly how this environment interacts with what's happening inside the cell can get very, very complicated. So there can be tens or if not hundreds of different proteins or chemicals in the cell that can participate in the regulation of whether the cell should respond in an oscillatory way or not oscillatory way to the environment. So this is very, very complicated. Of course, people have tried to write down very complicated rate equations, maybe like 50 rate equations. And sometimes when they are lucky with the parameters, they can actually reproduce some of the oscillations. Okay. So that's kind of the story. And as a series, if you try to think about what has been done, so we have these beautiful models like Kuramoto, okay? But then you face this issue of very complex molecular circuit, okay? Even though the phenomena is very simple, but maybe this shoe doesn't really fit the real situation, okay? And then people, really keep arguing which model is right, and many, many Science Nature papers published, but still the question remains, what's really going on, okay? So maybe if you can make some other shoe, which can, maybe not so, it don't fix the size, things like that, then if you have some kind of a overriding principle that allow you to kind of integrate different kind of information, then maybe that eventually we're going to reach some solution of, so on one hand, you should be faithful to the biology, but on the other hand, you can really explain the phenomena you observe. And this also can guide you in the design of targeted experiments in the future to really verify your hypothesis. So that's basically the idea. And the reason I talk about this at this meeting is we have many experts on the so-called non-equilibrium thermodynamics. And so I'm going to show you that actually there's a way to think about this oscillatory phenomena from the point of view of energy flow with some very simple construct. And this construct actually could provide this kind of shoe that's flexible but still can accommodate all the specificities of different biological systems. So the idea is very simple. We're going to look at the energy flow between the single cell and maybe the medium. That kind of, because in order for the cells to have this collective phenomenon, there must be cell-to-cell communication. So maybe the energy flow thinking can allow you to explain the oscillatory phenomena. And hopefully you will agree with me that the arguments we have constructed are very general. They are robust against the noise that affect the behavior of individual cells, and then also can take care of the cell-to-cell variations and could inspire further quantitative experiments. So our thinking actually is based on a very simple observation that actually if you look at the oscillatory systems, the individual cells, very often they adapt to the signal that mediate the communication between different cells. And we know adaptation is very common in biology. The cells can adapt to the chemical environment, to the mechanical stress, and even to light. And the adaptation can be very simply explained. So basically, if you have a cell in some external environment, and then you modify the environment in a step-like fashion, for example, particular chemical that the cell can sense, then you change the concentration of this chemical at some t equal to 0 by a certain amount. Then you're going to elicit some response by the cell in terms of the activity of, for example, some receptor or some protein. And then adaptation simply means that when you have a change of this environment, then there's going to be a transient response by the cell in terms of the activity level of some protein. And then after some time, it's going to return to its normal activity. Just like when we walk into a darker room, and initially you probably don't see much, but after a while you're going to adapt to the new environment. And there have been models that try to describe this phenomena. I'm going to lead you through one of them, a very simple one. So basically you have a signal, and then you have this observable that belong to the cell that can be observed and respond to this signal. But this observable is under the influence of potentially very complex molecular network inside the cell. But the end result of this whole thing, what's happening? A lot of dealings, a lot of activities, but at the end of the day, you're going to produce this kind of phenomena. And this response alone can be used to understand the collective oscillation in cell populations. So, so we're going to motivate our thinking with a very simple model of adaptation, which can reproduce the response I just showed you. So basically, you only consider two variables. This variable A, we call A, which is a direct influence of the signal in the medium. And then there's some kind of internal variable that allow the adaptation to happen. So in the real situation, there can be a bunch of internal variables that can, when this activity variable is changing, then it's going to excite some internal dynamics, but at the end of the day, as I said, then this activity will return to its normal level. So in the model, we consider this external environmental variable couples only, affect the behavior of the cell only through this observable A. And then from the second equation, you can see that this internal variable will stop changing only when this A returns to its normal value, A0. So this is really the key to understand adaptation, that the internal state will keep changing until this A that interfaces with the environmental variable come to its original value. Now, so this equation is linear, so it's very easy to solve it analytically. So for example, a stepwise excitation, then you're going to have a solution, delta A, which is given by this formula, with two these numbers, lambda plus and lambda minus, and all the college students in India can solve and find the expression for these two eigenvalues. And then in the model, there are actually two important parameters. This omega 0 defines some kind of time scale. And then Q is kind of a quality factor that has to do with the ratio of the characteristic time for A and characteristic time for this internal variable M that control the dynamics of A. So you can take this expression, and then for different values of Q, then you can plot out the response. So when Q is small, it's actually when it's less than 1, then you get the kind of response I just showed you. When you have a signal that has a stepwise jump, then you have this kind of response. But when Q is greater than 1, then you have an oscillatory response. So Q, in a way, is like telling you whether the system is underdamped or overdamped. Now, so this is how people normally look at adaptation. But you can also look at it by considering the response under a periodic stimulus with a single frequency. So in that case, the response will be proportional, at least in this linear model, to the strength of this oscillation with a response function, which you can also calculate very easily by solving this linear model. And you get this formula. Okay, the dependence on frequency is in the denominator. Okay, so again, this characteristic frequency, omega 0, appears in the denominator. So what is important is there are two different kind of characteristic behavior for the frequency less than omega 0 and greater than omega 0. So if omega is greater than omega 0, then actually, so this number, this ratio will be greater than 1, and the second one will be less than 1. So you have a positive number here. Okay. So that means if you look at the sign of the imaginary part of this response function, it's going to stay positive. Okay. On the other hand, for omega less than omega 0, then you have the opposite happening. The imaginary part of the response function in frequency becomes negative. And what that means is if you write this complex number in terms of amplitude and the phase, then the phase becomes positive for omega less than omega 0 in this shaded area. Okay? So what this means is that we are in a kind of a unusual situation. You have a signal, and then you have the response. So if phi is positive, that means the response can lead the signal in phase. So normally the response should lag behind the signal. Okay? But for this adaptive system, and the phase lead becomes positive when the frequency is less than this characteristic frequency. So this is one feature of this adaptive circuit. Now, another feature, so basically there is one particular frequency, that the sign of the imaginary part changes. And the other obvious property of this expression is that when you send omega go to 0, then this term on the denominator blows up, and then the response function will vanish. So I'm going to show you, yes? No, it doesn't happen. I will show you, okay? So actually here for adaptive system, you have this property that this response function goes to 0 when the frequency goes to 0. This is actually critical, as I'll show you in the next slide. And then from this property alone, you can show that the second property will generally hold. And when you have the second property, this then allows us to understand this oscillatory phenomenon, which has to be in non-equilibrium. So it turns out that this phase lead phenomena, just to answer your question, has to do with non-equilibriumness of the circuit. For equilibrium system, this cannot happen. So if you have underdamped or overdamped oscillator, after some, it can driven by thermal noise, then in the phase, you will not have this kind of property. But anyway, so the argument is actually very simple. It's just one page. So you can, in general, write down when you have, for example, a stepwise signal switched on at time equal to 0, then you can look at, because it's a noisy system, we look at the average response of this observable to the signal, and it's simply given by this expression, where here you have the integral of the response function up to time t. Okay. Now, we assume the system has the property of perfect adaptation. So, which means when t goes to infinity, the activity level returns to its pre-stimulus level. Okay. So these two terms will cancel. That means the integral. This can only happen if the integral vanishes. And the integral actually can be identified with the omega equal to 0 component of the Fourier component of this function. Okay, so for perfect adaptation, then the response function in frequency at omega to 0 must vanish. Okay. Now, if that's the case, then I think all of us know the Kramers-Kronig relation that can, due to causality, that link up the real and imaginary parts of the response function. In particular, the real part is given by integral of the imaginary part. And you look at this expression at omega equal to 0, so left-hand side need to vanish. And this omega also enters the integrand, but when omega equal to 0, it disappears. So you have the imaginary component of the response function times, so it divided by omega, which is positive number. So in order to get 0, then this imaginary part of the response function must change sign at least once along the frequency axis. So this tells you that if you have an adaptive circuit with perfect adaptation at least, then you must have, in some frequency range, this phase lead behavior. Okay? Now, if your system is not perfectly adapting, but nearly perfect adapting, then by argument of continuity, this statement should still work. Now, you can also show from just fluctuation dissipation theorem, in which case this imaginary part of the response function is related to some power spectrum, which has to be positive. Okay, so if the system is in equilibrium by virtue of the fluctuation dissipation theorem, then this cannot happen. Okay, so this is the theory. Now, the next thing we do is try to suppose your circuit has this property. Can it be used to drive the signal? Okay, so we then need to have an argument that adaptive circuit can output energy when the stimulus has a frequency in the range where the adaptive circuit has a phase lead. Okay? So to do that, we need to first introduce a coupling between the signal, the environmental variable, which may be the concentration of some molecule, and our observable A. And this can be done if you are good at StatMech. Of course, each case you have to do some exercise to do some calculation. And here I'm showing you, I'm not going to have time to go through the details, but this is something that can be done. For example, if the way the cell interact with some chemical in the environment is through the concentration of some ligand, and the ligand molecule, basically you can treat it as an ideal gas. So when it binds to the receptor, then it's going to have some energy. When it is outside in the solution, it's going to have some other free energy. Okay, so it's going to be some free energy change when it is outside or in the bound state. And the energy on the bound state is going to depend on the value of this internal variable A. Okay, so this particular case, you can actually work out everything in detail, and that's going to give you some kind of a thermodynamic potential that depend on the concentration of this signal molecule in the environment, and also this internal observable A. Okay, so in general, I mean, you can consider other cases where the coupling between the cell and the environment is not through this kind of near equilibrium process. Then the argument doesn't quite work. But anyway, at least in many cases, you can do this. And that's what we assume. So suppose you have some kind of a free energy that describe the coupling between your signal and this observable that reflect the internal state of the cell. And then you can consider the energy exchange between the cell and this environmental variable for the particular case of a periodic perturbation. So in this case, you can actually, using the standard formula, we have experts like Udo here that allow you to write down the power or the rate of energy flow between your system and this environment. And then some simple calculation for some linear coupling, the simplest case, that give you this formula. Okay? So in the formula, you see the imaginary part of the response function at frequency omega. So if this guy goes negative, so this is the work, the rate of energy exchange into the system. Okay? So when this is negative, the system actually outputs energy into the environment. So this allows us to then build a kind of overarching scenario for how this auto-induced collective oscillation can happen in a cell population by virtue of this kind of energy overflow. So what's happening inside the cell can be very complicated, but if the signal only interact with this particular observable, then this energy, so you can write down some dynamics for this environmental variable from this energy point of view. So this is what we did. So for individual units, you can start with this very simple linear model I just explained. And then for the population, then you can write down some kind of a dissipative dynamics, but including the coupling through this kind of thermodynamic potential with the cellular variable A. So if you have a population of n cells, then each cell will contribute a term like this to the dynamics of this, this signal concentration in the environment. So here we include a cubic term. It's not necessary for explaining the oscillation, but important for explaining what happens after the kind of instability that takes place. So if you adopt this set of equations, then you can see that there's an effective coupling strength, which has to do with how this signal affects the dynamics of this observable and how the observable affects the dynamics of the signal, and also the number of cells in the neighborhood. So this is really some kind of a mean field level model. And because we are interested in explaining the onset of oscillation, so this is sufficient. But we know that in real situations, sometimes you can have waves. Then for the dynamics of this intercellular signal molecule, you have to include some other terms in the equation. So then we so when my student took this model and did simulations and look at the behavior, the collective behavior of the system at different values of this M bar, then indeed he see that when this coupling strength is weak, then there's some noise in these equations. You see some random fluctuation, but not like collective behavior. But when this coupling parameter becomes sufficiently strong, then you start to see oscillations. Now, the cubic term, I didn't really explain, and we don't really know where it comes from, but it's needed if you want to explain that experimentally, people observe that when the oscillation amplitude becomes stronger, the frequency also increases. So in our model, to see that happen, then you have to include some cubic term in the description of the dynamics for the signal. And there may be other ways of also getting this effect. But if you don't have this cubic term and put some nonlinear term in the dynamics of A, then you actually see the opposite phenomenon, that after the onset of oscillation, the frequencies start to decrease as the coupling strength increases. So whether the frequency increases or decreases as the cell population becomes bigger and bigger can depend on some specifics of your model. But it seems that most of the experiments that we found in the literature show that the oscillation frequency increases as the cell density increases. So being a good student, he also did some simulation which are more close to the experimental situation. So he considered a heterogeneous population of these cells. So he mixed these cells together with different Q factor. Some would show this overdamped adaptation, some underdamped adaptation. And then he put them together, and then actually this population as a whole still can oscillate when the coupling strength becomes sufficiently large. Now, if you want to understand this onset of oscillation in detail, this can also be done within a linear stability analysis. So basically just take our equations, but ignore this cubic term in the dynamics for S. Then you can actually do an exact analysis on this collective mode. And you have actually 3 roots, 3 eigenvalues to this 3x3 matrix. So here, depending on the value of Q, then you can have different kind of bifurcation phenomena. So this can be easily worked out. But for any value of Q, eventually, so this is showing just the real and imaginary part of this eigenvalue. So basically, eigenvalue on the complex plane, there's 3 of them. They are shown in different color, but the red one in this case, I think is hidden somewhere. Okay, but anyway, so this is kind of an exercise you can easily do. And then the onset of oscillation happens for some particular value of this coupling constant when the real part of one of the eigenvalues cross the imaginary axis, so becomes positive, and the system becomes unstable. So basically, that's all I want to tell you this afternoon. So, so the first thing we found was for an arbitrary adaptive circuit, then it generically shows a phase lead over the signal in some frequency range. And then from using the argument from non-equilibrium thermodynamics, then you can show that this phase lead actually corresponds to the cell doing work to the environment. Okay. Now, once you realize that, then you can easily imagine, because these cells, they are pushing the environment at least in some frequency range, and this can lead to this auto-induced oscillatory phenomena. So even though this doesn't tell us much about the underlying biology, but we have actually looked at many different examples in the literature. And almost in every case, we can identify, I mean, in many cases, people know very little, but in some cases, people know quite a bit. Not to the detail of all the what's happening inside the cell, but they can identify the signaling molecule, signaling channel, and also this first contact inside the cell that couple to the signal. Okay? And that first contact really, in the cases we looked at, show this kind of adaptive behavior. And now if you take our story seriously, then you can start to think about doing experiments and start to understand the details of these particular systems. Some of these are listed here. So thank you very much for your attention.
Okay, it's really intriguing thoughts, Lei Han. I have to admit, I didn't fully understand why you need this stochastic thermodynamics energetic consideration. I mean, on the one slide, you had 3 equations of motion for A, Y, and S. And you could have written them down, presumably without ever talking about energetics.
Yes.
That's one question. The second question is, when you think about energy flow or the cell putting out energy, I mean, naively, I would expect perhaps that most of energy is immediately dissipated in the surroundings. So isn't it rather than perhaps some signal molecule is again leaving the cell? And
okay, very good questions. So first of all, actually, I mean, if you actually have enough knowledge to write down these dynamical equations, and that's what people have been doing for specific systems, then of course you just solve them, and then suppose everything is correct in your model, then you will reproduce what's happening. Okay, but in terms of understanding, I think this kind of energy flow argument will give you another way to look at, not by just solving, really just solving the equations, but also, understand in some more simple terms, in more intuitive terms. What is? Oh, this is okay. That's kind of connected to your second point, and here, this, of course, the cell dissipates energy in many different ways. So now here we are looking at a particular channel where the energy flows out of the cell. It's not that actually this normally should not be the major dissipation channel for the cell. Okay, but it's enough to explain. Because for something to oscillate, then it has to be driven. It cannot be in some equilibrium. So this provides an argument that so this the signal molecule actually otherwise it's in some equilibrium, just some particle in the solution. You can treat as ideal gas, whatever. But in order to generate some non-trivial behavior, non-equilibrium behavior, we have to drive it in some way. So this is give you through this coupling with the cell. Then actually in many cases we haven't got to the stage that for every example here, but for some of the examples, actually the numbers actually work out. In particular, many of the cases, they already have the dynamics as you mentioned. And then, but if you look at the model they have for individual cells, it is just has some adaptive behavior. So we can kind of circumvent all these numerics, okay? But just look at the response to this periodic signal and already build this story. Now here, it's kind of a spontaneous oscillation. So now if you assume the cell, the response to the signal has this adaptive behavior. So that itself means this circuit that coupled to the signal is a non-equilibrium circuit.